Okay, everybody. We're ready to start the session. So people would need to sit down and be quiet. So I guess Michael just volunteered to be note taker. That worked well, great. Thank you very much. Aaron is a JavaScribe. And Spencer is unfortunately not here, but I already beamed him into the room, so he will co-chair from the Meet Echo, I guess. Yeah, and we're ready to start the session. This is the TSV area session at IETF 102. Let's see how that. Oh, how do I get this working? Oh, it is working. Do I have to eat it or no? So welcome again. This is the node well. It also applies to TSV area, even so there might be less document discussions. But probably you've seen it already this week. This is the agenda for today. Yeah, again, thank you for Aaron to scribe for Java. Thank you for taking notes, Michael. We have 15 minutes for the TSV AD overview because we have the overview and we also want to talk a little bit about AD experience and what we do in our daily life, so you can get an impression and then candidate for the next AD position that's available in March. And after that part, we have 3 presentations, and we kind of cluster them all into deployment issues and considerations. The first one is from Christoph Pesch on multipass TCP and the difficulties to bring this into the Linux kernel. Then we have actually a presentation from Ian, which has a different title now, and I didn't update the slide. So this is on quick deployment challenges. And then the third presentation is on wire images and pass signals from Brian and Ted, which considers 2 documents which are under discussion in the IAB. And then if everything runs well, we still have 10 minutes open mic at the end. Any agenda bashing? Okay. As always, a big thank you to our review team. We're still kind of trying to get everything up to speed, but we see more reviews and we see those reviews in a timely manner, which is really important for us. So thank you for that. But we also still try to figure out how to optimize the workflow and kind of the reviews. So in case you're interested to become a transport area reviewer, you can talk to us. Or we might talk to you at some point. Spencer, if you have any comments, interrupt me, right?
Yeah, sure.
And this is the usual slide we have on the working group status from the AD perspective. It's a very brief, high-level view. So if you're a chair and you disagree, don't worry, or talk to us. From my side, I have a couple of working groups which are wrapping up their charter, which is very positive, I think. So we get some work done there. And then I have also some more long-lasting working groups which make good progress. The only thing I would like to mention here is that we changed responsibilities for IPPM. So that was Spencer's group and now it's my group. Spencer, do you want to comment on your groups?
Just to say that connection ID for Quick is really hard. And I think the other thing to mention is, we are looking at several groups that are, finishing up milestones. So we're kind of getting close to recharter or conclude for several working groups. So just kind of keeping that in the back of our minds.
Are you saying we're looking for more work or?
I'm not sure what okay. I think what I'm saying is that, that it would be good if we did not get my replacement starting in March, and then all the BOF requests start arriving in April.
True, very true. Any questions on this part? No. Yeah, we have also done some work. I think this is actually less documents than, for example, last time, but that's like, I think, in the normal variation. Also, there are a couple of documents which are under IESG evaluation currently. So that's the progress we made since the last meeting. Yeah, Spencer, do you want to go on this one?
Yeah, so we were contacted by Kit to talk. Basically, the BBF has been relying on TLS keep alive mechanisms in the NetComp server, and everybody post Heartbleed is removing support for that as fast as they can type. The suggestion was made around in the NetComp world about using TCP keep alives, and the SecADs were not happy about plaintext mechanisms for keep alives, and we were not happy about encouraging transport only keep alives for several reasons. So we had a couple of proposals there. One was, could they actually talk people into not removing RC 6520 support, which is humanly possible, but I wouldn't bet on it. The other one is just basically saying that they need to do application level keep alives anyway, because that's what matters. More broadly, we've been asked about providing some kind of consensus guidance about this that's not just, me and Maria and a couple of SecADs opinions. So, basically a statement that would recommend against using plain text keep alive mechanisms for secure transport sessions, recommend using application level keep alives to actually test liveness. There's a thread, TSV area list called statement regarding keep alives, and we would so there's been some discussion under that thread already. We would be interested in hearing more.
So I think Kent Watson, who started this thread, is in the room. Do you want to stand up for a second so people can see you and if they want to talk to you? So one question we also have is what to do with this statement, right? Is this something which we just need to write down and send an email somewhere? Is this a BCP? Is this something the IAB should figure out what to do with? Like any feedback on that is welcome.
Yeah, thank you all.
Kent from Juniper. Just to add to that, it's not just a statement about not using the TCP level keep alives, but also a recommendation for protocol designers to include keep alive mechanisms inside their protocols, which is many times an oversight.
Right. Thank you.
Okay, I go to the next slide. Yeah, this is also related work we want to point the transport area to. So that's a congestion control mechanism that was or is developed for COPE and mainly discussed in the core working group. But given this is a congestion control scheme, there will be presentation in ICCRG. So transport feedback is highly appreciated in ICCRG on tomorrow afternoon. I thought it's on Friday. Okay, tomorrow. Good.
Yeah, thank you in advance. So, I'm still the outgoing transport area director. My term ends in March. Martin and Mary and I have been working since 2013 to make the job doable. And there's a link in the presentation for what we told NOMCOM, which is actually pretty close to what NOMCOM is using for their position descriptions. If you just look this up on the NOMCOM page, please nominate freely and please give lots of feedback on willing nominees because this really matters. If you have any questions about the position, please ask. You could ask here now. Mary's in the hallways. Ask us on the TSV area list. That would be fine, or in private email. And again, thanks in advance.
Yeah, and I also thought I'd talk a little bit more about what doable means. Usually I point just people to my Pecha Kucha, but in this case, maybe more information might be interesting for you. So, I mean, what does the daily life of an AD nowadays, or transport AD, look like? And I think both Spencer and I, we spend like 15 to 20 hours a week. Might be sometimes more, might be less. The only problem I sometimes have is that's really 15 to 20 hours every week. So if I go to a conference, it will be more hours the next week. But yeah, it's still a reasonable amount. Most of this time is really reviewing in IESG evaluations. So it's reading drafts of all different areas, trying to understand as much as possible. And it's about, like, we have now a limit of 400 pages for each telechat. So there's a telechat every 2 weeks, which is about like 10 to 20 drafts usually. But I mean, also, drafts, right? If you have a 10-page draft, it's only kind of 5 pages you actually have to read because there's front and path matter and whatever. And then we have sometimes Yang models where you also don't have to read every line. So 400 pages is actually realistic here. If the draft is short enough and like not very related to transport, I can do like a draft in 30 minutes. But like if there actually is a problem and I have to understand things, then of course it takes longer. Still. Then there's also, of course, a little bit load that is related to the working groups. But we in transport only have 12 working groups, so it's like 6 working groups per AD. And I actually looked this up. We published 25 RSCs last year. So it's also a reasonable load. And many of them was actually on Spencer because it was one specific working group which was wrapping up a lot of work. So it's actually even a little bit less than that. Some steering is involved from time to time, but we also have very good experienced chairs who know what they're doing. So it's some steering coordination, some feedback, but it's not like a huge amount of time. There are other things the IESG is doing, like everything related to the IETF process itself. And we need people doing this in the IESG, but usually it really depends a little bit on who's interested in the topic, who has time to do it. So like I myself don't take up a lot of these additional responsibilities. It really depends on your time commitment. There's one thing transport is responsible for, and that's support registry. And usually that works on its own. So we have very good reviews there, but sometimes there's a question and then you have to care about it. But it's like in terms of time commitment, it's also not a huge thing.
Right.
Yeah, so that's my my day. Any questions?
Aaron Falk. For a brief unhappy period, I was on the IESG mailing list. Fortunately, somebody fixed that. How much of your time do you spend reading IESG email?
So I actually try to manage to keep my AD work on like 2 days a week. So for me, it's usually Monday, Thursday, and sometimes I don't read those emails the other days, or I have a very quick look. But I mean, after all, it's not that you have to read all the emails because it's like it's reviews, it's comments to the reviews. Not everything is relevant for you. So filtering out what's relevant for you takes a little bit of time, but still, it's like you don't have to read everything, right? So it's I guess it's an hour every morning. I don't know.
If I could, yeah. So what I ended up doing was splitting my ISG email into documents that I was responsible for, documents that I was not responsible for on telechats, and kind of everything else. So that allows me to prioritize a bit. The other thing I would say, and Maria's referred to this a couple of times, but there are things that the ISG needs to do, things that the ISG needs to worry about, but we don't need 15 people worrying about them. So, that would not actually help. So, basically, if you find some topic that you're the right person to work on, or there are 3 people that need to come up with a proposal for something, then you spend time on those. If that ain't you, you usually don't.
So I have to say, like at the beginning, it freaked me out a little bit to see all those emails, but like as soon as you figure out how to handle it, it's doable. Yeah.
Procmail is your friend.
Yes. So that's this part. I mean, like now would be a chance to ask more questions, or you can just talk to me in the hallway, I guess, if you catch me.
And seriously, we have limitless interest in talking to people and answering questions. Please don't be shy.
Okay, then we start with our first talk. Christoph is coming, great.
And just as we're starting this, I'm going to go ahead and beam off here so that people can use the mic line. If anybody needs to talk to me, just yell and I'll raise my hand.
Yeah. Okay. Hello. So this is a modified version of a talk that we have been giving last week at the Linux Network Developers Conference. This is work where we are working together with a bunch of people. There's Matt Martineau and Peter Christat from Intel, Matthew Barth from TSVAREA, and myself. And so Matt and Mathieu, they presented that last week at Linux Network Developers. And I'm presenting here a slightly modified version that shows more the IETF and protocol design impact on upstreaming MPTCP. As most of you know, MPTCP has been now an experimental standard for, I think, maybe a few years. And since the beginning, we always had a Linux implementation that was implementing a standard. However, it is still not upstream in the upstream Linux kernel. And some are surprised by that, and there are various reasons for that. And I will talk to some of those now. So the question is, why is upstreaming MPTCP actually so complicated? Well, first of all, for those of you who know the Linux kernel, the TCP stack, it is highly optimized, right? They can go up to almost now, I don't know, I think 100 gigabits per second for a TCP stream. Any addition of additional fields in structures incurs additional cache misses, which basically kills performance. An if statement will introduce additional branching. They are very sensitive to all of this, the maintainers of the Linux kernel networking stack, right? And because of this, the stack has become extremely optimized. So every change in the Linux TCP fast path is being scrutinized heavily. Then there's also the original implementation, the one where everything started off with, that we created back in the days when that Sébastien Barré, actually back in the days, for those who know him, created, and that I took over then. And this implementation, the goal was a bit different. Our goal was not to upstream it immediately. The goal was basically to have a way to quickly iterate and implement the standard as the standard was evolving, as the draft was evolving. We wanted to be able to experiment, to get quickly numbers out of this MPTCP implementation, to see how certain decisions in the protocol would affect the performance of MPTCP. So our goal was basically to have a non-generic stack and be quickly at iterating at the time. And also, we were researchers, so our goal was also to write papers and not necessarily to upstream code to the Linux kernel. Now, over time, this implementation has evolved into a more stable version, and actually nowadays there are, I think, millions of devices that are using it. People have heard of Samsung deploying it in Korea, and all of this is based on this particular stack. But all of those deployments that are currently out there, they are still very special purpose deployments where the system administrator who is deploying it has a tight control over how MPTCP is being used. Now, we want to evolve the MPTCP implementation in the Linux kernel so that we can actually more easily be integrated into the Linux kernel. And that means we have a few limitations. First of all, that means there can't be any performance regressions in the regular TCP stack. That's the non plus ultra condition. The second one is we want it to be maintainable and configurable. The current special purpose way of deploying MPTCP can't be done in a generic implementation. that might be used by Android and many other systems. And so we also want it to be deployable in a variety of deployments. So an ideal MPTCP implementation would basically look like that, right? You have the socket layer, below that you have an MPTCP socket, and then you have the TCP subflows over this. That would be, we have a clean interface between the different layers, and we would just basically send the data either over one or the other TCP subflow and receive it as well. That is the ideal MPTCP implementation. However, the reality looks rather like this. We have data structures sitting at each layer. We have callbacks from up and down, from one subflow to the other subflow. And all of those different interactions, data structures, and calls are making the upstream very complex. And I will show you how some of the protocol design decisions that were made have basically influenced this design and have led us to end up in this situation. So that brings me to the protocol challenges. And I must say, this is not to like kind of put the blame on one or the other. It's just like, well, because I mean, I was also part of the protocol design, so it's kind of, we all are kind of part of this. And also, this is just how one part of the protocol specification kind of influences certain decisions that need to be made inside an implementation. So first protocol challenge is that the data sequence numbers and the mappings, right? For those of you who know MPTCP, right, we have the two sequence number spaces. There's one sequence number space for the data that is being sent, and the sequence number spaces in the individual TCP subflows. And for example, the data sequence space, let's say here in this example, goes from 1, 2, 3, 4, 5, and we are sending segments. And let's say we send the gray part of the data, we send it on the left subflow, and the yellow part of the data, we send it on the right part of the subflow, on the right subflow. So this means for every segment that we send, we need to specify the data sequence mapping inside as part of the segment. The MPTCP protocol says that this kind of DSS mapping is specified inside the TCP option. That seems like a very obvious design decision, and it was at the time when we were designing the protocol seemed like a good approach. Now, however, if we want to implement this, it becomes a little bit tricky. One of the problems is, so we have the MPTCP socket who's basically holding data, and then we are pushing data down on one subflow. Now, if we have a clean interface between both, right, we are basically pushing data down this just memory allocation. Now, we need to kind of add to this, tell the TCP stack, hey, I would like you to write with this segment, this particular TCP option. And so the TCP stack would need kind of to call back into the MPTCP stack and ask, hey, what kind of DSS option should I write, right? This introduces a lot of back and forth between the layers. So the other solution that we would want to do is, well, why not just simply add this information about the DSS option as part of the metadata that comes with the data. And if you know the Linux kernel, it has basically the memory region that is holding the data, and then you have what is called the SK buff, which is holding the metadata. So the obvious approach would be, well, let's simply add the DSS mapping inside the SK buff. That is problematic for a few reasons. The first reason is that we can't just simply increase the size of this structure because the TCP stack is so highly optimized. Adding fields into a structure means potentially more cache misses, and the cache miss can go anywhere from up to 200 CPU cycles, and that will simply kill the performance. So it is basically forbidden to add anything inside this kind of a structure, except if you manage to do it in a cache neutral way. The second reason why, even if we would manage to somehow add this information into the SK buff such that there are no additional cache line misses, there's still a problem, is because the TCP stack can at any point decide to split the segments, split them in multiple parts, merge it with others. When TSO is used and it receives a SAC, the Linux TCP stack is going to split those segments in different pieces and might merge them back with others. So that means anywhere in the TCP code where we are splitting and merging segments, we need to make sure that the DSS mapping is propagated through the metadata as well. Again, meaning more if statements into the TCP stack. Another issue or challenge that we are facing is that we are transmitting signals on TCP options, and there's no clean interface in the TCP stack to basically propagate TCP options up to other layers. Usually TCP options have only a notification locally inside the TCP stack, right? Let's take the example of SAC. The SAC option will be taken care of by the TCP stack only. Same for the timestamp option, same for all the other options or most options that we can think about. Now, let me give you an example of how the use of TCP options for cross-layer signaling is a problem. Let's say we have an MPTCP connection with two TCP subflows, and one of them has basically a notification, my interface goes down. At this point, the TCP socket will be destroyed, and we now need to send a remove address on the other subflow. So that means first there's a notification coming up to the MPTCP stack, and then we need to push an information down on another TCP stack and telling the other TCP stack, I want you to send an acknowledgement with a very particular TCP option, right? Currently, there is no clean interface for those kind of things. Usually an application that is sitting on top of the TCP stack never tells the TCP stack, hey, send an ACK with this option, right? So that is something that is new and that needs to be built and added into the TCP, into the Linux kernel. Another problem now, you can see this on the receiver side when we are receiving TCP options, right? For example, we receive the remove address option, which means you need to kill the other TCP subflow. So we receive a TCP ACK with a particular TCP option. First of all, this TCP ACK looks like a duplicate ACK and usually gets simply dropped by the TCP stack. So we need to already cut this behavior in the stack. Then we need to pass the remove address option and propagate it up to the MPTCP layer so that ultimately then the MPTCP layer can kill the other TCP connection. So again, we need cross-layer signaling between the layers that is originating from a TCP option. So there are many of those signals inside an MPTCP, inside the MPTCP specification, and each of them needs different kinds of behaviors and different layers in the stack. And so it's kind of tricky to make sure that all of this gets consolidated into a single point. All those cross-layer signaling are basically a major pain point for the MPTCP implementation. So how are we trying to fit the MPTCP stack into the networking stack in Linux? So first of all, having this layered approach is very clean. It fits very nicely into the existing stack. We can create a socket with a certain type that basically is sitting like a shim layer between the TCP flows and the application. There are some in-kernel interfaces that allow to send data together with the metadata, with the SK buff, and also to read it as well. This kind of design fits very well. The challenge comes later on. Now for the cross-layer interactions, one would obviously think that adding this like this through indirect calls, because that allows to have a generic approach. It allows to make the TCP stack not MPTCP specific, which is something an operating system always tries to avoid. However, since Spectre and Meltdown, indirect calls have become increasingly extremely costly. And so the Linux kernel developers and maintainers are basically avoiding indirect calls. So indirect calls are no more a solution to have an generic implementation. And the other problem that I already mentioned is the SK-BAF non-extensibility. If we want to add any kind of metadata to a packet or a segment that is being sent, it needs to be done in such a way without increasing the size of the structures, which is very tricky. So what are the next steps for us to target upstreaming? So together with the people from Intel and Tesseract, we have now been working roughly for 1 year on it. And last week we presented our plan and our challenges that we are facing in a more detailed presentation than the one here today. We received very supportive feedback from the NetDev community, telling us that the TCP maintainer said that he actually really wants MPTCP to be upstream. So that was very positive feedback for us, and he gave us also some suggestions on how to handle, for example, certain issues like the skbuff non-extensibility. We started to reduce MPTCP to the least minimal viable implementation, removing all the features, just making MPTCP, bringing it all the way down to the bones so that it can just interoperate with another implementation, but without supporting any feature. The cross-layer interactions, we are trying very hard to consolidate together in one single call so that we reduce those cross-layer interactions, and we hope that we can make them in an asynchronous way so that we don't need to basically block on those kind of calls. And we received a suggestion on how to do the skbuff extension in a cache line agnostic way. So this project, there are a few links out here on the slide, and you can check it out. Yeah, go ahead.
I'll let you finish. Do you have more?
Just one slide for lessons learned.
Go ahead.
Okay. So in terms of lessons learned, specifically with regard to standardization, here's what, in my opinion, is one of the things that we should maybe keep in mind in the future. One is obviously that protocol design has a direct impact on the implementation, right? Any decision that is being made can impact the upstreamability or the widespread deployment of the protocol. One thing that is very tricky, in my opinion, is that TCP options should only be used for, let's call it unreliable signals, and not for signals that are linked to the payload. Because in an implementation, it is extremely difficult to make this metadata move along with the payload. Because the payload, in the end, inside the TCP stack, it can get split, it can get merged with other segments. And so many TCP stacks don't have a real notion of fragments or segments, right? And so it's best, the TCP options are best used for just unreliable signals, like a SAC option, right? It has no relation to the data itself. It's just purely related to the TCP header. Cross-layer interactions should at best be asynchronous, so that the signal that is coming in through the TCP option can basically be queued and can be read out of the TCP stack later on. If it's asynchronous, it simplifies the layer separation between the different stacks. Also, one lesson that also I learned, because I was very much involved in the prototyping at the beginning of the Linux MPTCP implementation, is that the prototyping is very different from widespread deployment and integration in an upstream kernel. During prototyping, you try to be quick, you try to iterate fast, you do shortcuts, you do sometimes nasty things because you want to finish a paper before the deadline, and you want to get some numbers out of the implementation. And so all of this is extremely different from the deployment in a real, in a large scale and in a real generic way. And now
Thank you. This is very interesting. I learned quite a bit. I don't know if I would replace your first bullet, but I would certainly add a second bullet that says the converse, which is implementations directly impact protocol design. It seems to me that what you learned, the story that you're telling is that there were a bunch of design constraints on the protocol that you didn't know when you were designing MPTCP, that you discovered late on, and that caused you to have to do a bunch of rework. So would you agree with that?
So you mean that in the end, the implementation shape the protocol as well?
I'm saying that you learned things like the buffer, the cache access efficiency was a constraint, and you needed to change your design to accommodate that. And maybe if you'd known that early on, you might have made different design decisions. So I guess let me ask it differently. If you had known then what you know now about the constraints, would you have designed the protocol differently?
Yes, absolutely. Yes.
Okay. So are those constraints written down anywhere? And do you think they could be written down? And do you think you could write them down?
Not that I am aware of. They are mostly on mailing lists, on feedback coming from the maintainers, right? So I'm not aware of any like written down list of constraints. Might be worth to write them down. I agree.
It seems for people who want to get the technology, I mean, we spend a lot of time in the IETF these days talking about making our stuff deployable, right? That's one of the reasons we're talking about GitHub, right? We want to sort of reduce the distance between us and actually rolling things out. And I think you've identified a pretty big issue here, which is like we're designing stuff that, you know, that the maintainers may look at and say, you know, you can't do that. And, you know, that's a real impediment to getting it out there.
Yeah,
so
that's a good point. One question I would have then is like those kind of constraints are very Linux specific. Other implementations, like in iOS, we don't have that problem. We don't, because we kind of don't care, right? So, well, there are certain things where we can say, okay, the benefit of adding MPTCP overweights the cost that it is introducing.
Great. We're not yet.
Hi, Brian Tremel. I guess we're just going to go down these bullet points. So I want to make a point on point 2. I expect 2 more people to get in line behind me. So this is a really interesting lesson learned. TCP options best used for unreliable signals, right? Like, so the farther away you are from the core specification, the less you can rely on it working everywhere. And I think we kind of know that in, you know, I mean, like we have, you know, the hops and the MapRG stuff. We've dug into that. These things we're measuring more and more. I think sort of a lot of middle box measurement work was actually spurred on by MPTCP, right? Because that's what it started as a let's extend the protocol, and it turned into a whole bunch of work on how middle boxes break the protocol. There seems to be kind of there seems to be like a protocol architecture truth hiding behind this, and it's something we should probably consider moving forward when we're talking about extensibility in Quick, for example. So thanks. I've learned a lot too.
Yeah, one question is like when we start adding multipath into Quick, and there will already be a bunch of implementations out there, and they will need to remain stable and performant. Will we be able to add multipath into Quick easily? That's a question.
I think so, because we can actually design, you know, I mean, there's been a lot of thought now in what we found out this morning is probably going to be called version 2, so that when we go into version 3, that we're laying some of the groundwork now, and CIDs make it easier, for example,
sure.
Right? So.
Possibly difficult question, Lorenzo. So, how much of the stuff would you say is specific to SKBUF, RCU, and all the stuff that's specific to the Linux kernel? Like if you were to take these learnings and you were to take them to the iOS user space networking team, how different are they? I mean, how directly applicable are they? Is this something that we do? So there could be, I could see 2 things. First of all, you write all this down and you come here and people don't believe you. Well, they don't believe you anyway. So, okay. But at least you're right. But if you write it down, but if you write it down and he says, look, dude, like in my implementation, it's entirely different. Like the scheduling constraints I have are completely different. I don't have this locality problem because my architecture, I have something else, right? Have you compared notes with the people working on the user space implementation to see? Because if you take this and you take it into DPDK, maybe it's entirely different again. Or if you use AFXDP to do it in user space, which you maybe can do in 417 actually. Have you considered that actually?
Not directly.
Okay.
But I agree with you that like different implementations have different contexts, and it's not that easy to generalize all of that, right?
Eric Kinnear, Apple. Very briefly, yes, we have compared notes. We're all the same team. But I think your point still stands in general, is it would be really nice if we could take some of the stuff that we've learned and seen and kind of put that out there as more of a, as we go forward in the future and look at MP Quick or other areas of protocol extension or even just first time design, where is that going to things? Exactly. How can that apply?
Yeah, if we write something like this down, I think we should try to make it implementation agnostic and try to, not make it specific to Linux or iOS or whichever stack.
Ian Sweat, Google. I had one comment on the MP Quick thing. We actually tried to take a whack at that early on. And it turns out if you have your software structured well, it's not overly complex, and you maybe at max introduce one extra pointer deref in the worst case scenario. But like overall, the fact that in Quick you're acknowledging packets with packet numbers instead of segments in sequence space means that the type of data structure that is conducive to multi-path Quick looks more like two entire sets of SK buffs. And so you don't need to add things to the SK buffs. You just need two parallel data structures, each indexed by packet number.
When they do it doesn't hurt when you do it there for he said his implementation. Well,
No. Oh, no, not for TCP for Quick. I'm saying it's easier to implement in Quick because of the natural packet number versus sequence number difference. That's the core concept.
And Lorenzo, another difficult question now that you're here. How much of this do you think is due to the fact that decisions were made in the past that were absolutely in the best interest of the Linux TCP stack, and it's gone really, really, really far down the path of being highly optimized, and all those decisions, like if you'd had like multipath in mind at each of the decisions points, like how much do you think would have cost more? Because like I can imagine that at some point they were faced with a trade-off, and if they'd had multipath in mind, they would have picked A instead of B, and but they picked B because it's like, well, and how much do you think that is? And it's a difficult question, like I said.
Yeah, it's hard to know how much this has been influenced those decisions, but yeah, would have been interesting if we would have gone directly upstream and taken all those things into account.
I guess does this mean that we should, if we want it to be deployable, should we be saying, should we not ever or try not ever to say, this is just an extension on existing protocol, so it's going to be easy to implement, right? Because we might have said it's already there, right? The code's already there. But if you have the structural problem, then you can't get into a real world implementation because you have a chicken and egg problem, and the people who maintain that implementation is like, no, you can't make me 3% slower. Because because it cost me a lot of blood, sweat, and tears to get that 3%, and it took me a year, right? So, yeah.
My name is Tim Shepard. I actually just reading this. I know you mentioned Linux a little bit, but just reading the slide, I was actually thinking this is more about decisions that were made in the MPTCP working group, which might have been made differently, and I think you said something along those lines.
Yes, this is about for example, the fact that the TCP options that we are currently using are linked to the payload itself makes things hard. So that was a working group decision to design the protocol that way, and that makes the implementation very difficult.
Right. I remember there was a MPTCP working group meeting, which I was sitting there listening to, where they were deciding to either use TCP options or put stuff in the data stream of the subflows. And it was, for the people in the room, it was overwhelming use options, but there was one person, I can't remember who it was.
Michael Scharf, I think. Michael Scharf.
Oh, okay. Thank you for remembering that. And I thought he had compelling arguments, but essentially very few people, a lot of people shrugged. I think I was one of the ones shrugging, even though I found his arguments compelling. But there was a very large number of people who were like, we're definitely going to use options because it's multipath TCP, and so it should use TCP options and blah blah. And so and the decision was made, and here we are. And I'm wondering, could we think about MPTCP v2 that doesn't try to do it all in options?
I think we have something to do in the working group then. But the thing is, the option story is not the only problem, right? It's not like, this is like has doomed MPTCP or anything. It's just one of those things that makes it kind of tricky for upstreaming, right?
Yoshida, one comment is, the overhead of option is not only factor of the using option. Because performance is not only focus of the when we design the protocol, in my understanding. So yeah, performance is not good, but when we make an MPTCP, we think other factors as well. That's the result, right? And then that's the one comment. And then the other comment is, then when you design MPTCP from scratch, you want to put the information in the payload. That's your conclusion?
I would put the DSS sequence number in the payload, the data arc in the option, right?
Can we defer redesigning MPTCP to the MPTCP working group at this point and move on? Thank you. Because we're running a little bit out of time, but I'm happy that people are interested. Thank you very much. So Ian, your slide's up.
Is this one? Perfect. Okay. Oh. As it says on the slide, I am Ian Sweat from Google. So this is actually taken also from a NetDev talk, but this is much more truncated. The NetDev talk talked quite a bit about the history of deploying Quick, including a few more performance numbers and some of the other data. But that all that information pretty much has been presented at the IETF, either in the form of a BOF or some other kind of working group activities, Quick working group or otherwise. So here I'm actually going to focus mostly on kind of deployment in terms of like CPU and software architecture and interacting with Linux and kind of some of the similar issues that Christoph alluded to. So at the beginning, as an overview, Quick is a protocol for HTTPS transport. At least that's how Google had it deployed starting in 2014 between Google services and Chrome and mobile apps. There's some rebuffer rate improvements, some search latency improvements. It's about a third of Google's traffic as of SIGCOMM in 2017, 7% of the internet. And obviously there's a Quick working group that's very active. So all of this is good motivation for us deploying this more widely, but there are challenges with that. So here's our ramp up over time from the SIGCOMM paper, but the thing I want to call out here is during the March to August timeframe, where it was all flat and there was no increase in rollout, we were just furiously working on CPU improvements. So some of these were kernel related, many of them were just internally in our own software. And that's why you kind of see a long period of flat and then a huge jump right afterwards where it goes from about 15% of our traffic to 30 in the course of a month or so. And so I'm going to talk a little bit about how we did that and how we're continuing to work on new things to make things even better. So initially, the major sources of CPU, crypto is a fairly large one, although certainly not as large as some of the other ones. But Cha-Cha 20 at the time was fairly slow originally. We did not have the AVX2 assembly in. That seems to make a ton of difference. So just FYI, like Cha-Cha doesn't have to be slow, but you probably do need a relatively modern Intel processor. And so that's exactly what we did. The other thing we did is actually we're using in-place encryption, at least for the sending path. That consumes a little bit less memory bandwidth and appears to actually have a few percent CPU gain. It's a little bit surprised that it's true, but it turns out to be true. We haven't tried it on the receive path yet, but I suspect it would work equally well. We thought about doing scatter gather. And kind of copy and encrypt all in one operation. It turns out the APIs for that are more complicated than doing in place. So we stuck with in place. Just FYI. So sending and receiving. This is where like the vast majority of the cost goes. So on Linux, it's not uncommon for this to be sending to be something on the order of 25% of CPU on a machine. Receiving maybe like 5%, 10%. at the worst case scenario. On Android, I've seen numbers over 50% for sending. I've also seen that on iOS. So it can be pretty huge. Currently, our two biggest kind of, one is new and one is older. The older one is Packet RX Ring, which is a receive side optimization. That allows us to share a memory buffer with the kernel. Packets get very efficiently read into that buffer, and then we just get an upcall and says, like, here's a ton of data, like, go at it. And then when we're done, of course, we give it back to the kernel and rinse and repeat. So at least in terms of profiles, this is not quite free, but shockingly cheap. I don't know why, but it is super duper cheap. So when it's available, it's quite appealing. UDP receive in general is actually not that expensive. It was more expensive when we started the Quick project. But Willem and Eric Dumazet made some really nice optimizations on the UDP receive path over the last few years. And so when we've done recent benchmarks, it was only a few % difference between RX Ring and UDP receive, whereas probably more like a 10% difference when we first launched it. The other thing that has been added more recently, about May timeframe, is something called UDP GSO. That allows the kernel to do segmentation, not fragmentation, but segmentation, where you give it a very large UDP packet and it basically segments it for you. Now you have to do everything correctly because it's very important that the quick packet boundaries line up exactly with where it's going to segment it. Otherwise you end up with like internet garbage. But it turns out this isn't super hard to implement. You just, you have a max packet size and you put that in and like everything works. And of course, we haven't really been exploring it too much, but kernel bypass is still a potential option, especially on the receive side. And I know that like we've been talking with Apple about some of their newer APIs, particularly for iOS 11, or is it 12? 12, sorry. And some of those look very promising from a performance perspective in terms of client-side performance. So internal state, all of the issues that were highlighted before about multipath and the challenges of getting multipath in, our data structures are not nearly as optimized as the Linux kernel as you might expect, because we have been around for 4 or 5 years and gone through over 40 quick versions, and they've been around for 40 years or so, maybe not quite that long, but a very long time, and had a lot of people working on it for a long time. So we're still working on improving cache efficiency, improving our data structures, and minimizing copies and allocations. We're pretty good on copies and allocations at this moment. Cache efficiency is actually still a major problem. Like there's still some pointer following and visitors and such. And I think we've pretty much gotten rid of all the linked lists or anything else that's, of that nature in our code, because pretty much you want as much as possible to be in, contingent or coherent memory that's like, in large blocks, and you do not want to be like following pointers to pointers to pointers. Great. So the last quirk is Quick has encrypted acknowledgements, unlike TCP. That does defeat some of TCP's kind of receive side aggregation that it can do. I believe that's part of the GRO mechanism, if I remember correctly, or at the very least, some middle boxes do it for you, whether you ask them to or not. And so do some Wi-Fi access points from what I hear. And so, in general, it's possible in Quick to get fewer acknowledgements, but also more importantly, you don't have to do decryption, and they're relatively simple to process. So our solution for that is we send ACKs less often. So by default right now, we are sending ACKs every quarter RTT or every 10 packets, whichever comes first. So at least with BBR, that turns out to work rather nicely. It doesn't actually give you better congestion control by itself, but it saves enough CPU on the client side that you end up actually with a slight increase in bandwidth. It's kind of crazy, but it's true.
Lorenzo Culletti, it turns out that if you send 1 ACK per packet or 1 ACK per 2 packets, and you're receiving very fast on Wi-Fi, you run out of transmit opportunities. And so ACK decimation actually really helps, even though you're doing nothing else wrong. And the other side of the coin is, people have tried to get that into upstream Linux as well. It's like, we don't have this problem. Data centers go away. and so we need something that auto-tunes. So I guess that's one of the advantages of doing it out of the kernel.
So I want to talk a little bit about how we're using sockets. We've gone back and forth with our kernel team about kind of what the recommended approach is in the server-side application. It's not clear that this should be the recommended approach for everyone, but it's sort of what they came up with. So the approach is to use a socket per thread. Sorry, I should clarify, a receive socket and a send socket separately per thread with SO reuse port for the receive socket. So it splits all the traffic kind of stably for you into the number of threads. Obviously, you can't change the number of threads after you start up the server, but that's usually not a huge constraint. We do use RxRing, but you still, I think, end up having, actually, well, with RxRing, I guess we're using a BPF, but yeah. I think SO reuse port works with RxRing too. I can't remember. Because RxRing is just packet sockets. So the app dispatches based on quick connection ID. So, you know, it gets all these random packets for various different connections, dispatches to the correct connection, you know, hash table, standard stuff. And, you know, at least initially what we did is we just had used straight SO reuse port. And if a packet landed on the wrong thread, we would just toss it to another thread. So that adds a fair amount of contention. But NAT rebinding and connection migration together are much, much less than 1% of all connections. So if you're doing this for, you know, 0.5 or 0.4% of all your packets, it's somewhat acceptable. In the world, if we thought we were mostly going to have connections that were longer lived or a lot more connection migration, then that approach might be a little less viable. So, and then the other thing that Lorenzo got out of me is that, yes, you can also use a BPF for connection ID based steering. And that's pretty simple. Yes, so we're using a socket per thread for sending. A send socket per connection is mostly impractical from what we've tried together. We've actually been going back and forth this week on kind of what the right API for that would be. But at least my current understanding is that in Linux, none of the APIs do quite what you would like. So you can't kind of follow the standard TCP accept and then create a new socket sort of like pattern. That pattern doesn't quite work for sort of connection-oriented UDP sockets. If I'm wrong, then please correct me, but this was certainly true when we kind of started this project 3 or 4 years ago. Also, it turns out like a socket per connection is not necessarily that beneficial. There's a fair amount of like state overhead and such per socket. And we're not really using it for anything at the moment. We're not using like pacing offload or anything like that. And so it's just basically we're just looking for the cheapest way to get a packet onto the NIC as quickly as humanly possible. I should mention, since we're sharing a socket among all of these threads and all of these connections, we do use application layer pacing. And we only pace 1 millisecond into the future, which is fairly comparable to what Linux does internally in the FQ pacing QDisk. And that allows us to not have an insanely large socket buffer. Otherwise, if we sent 10 or 20 milliseconds in the future, we would need multiple megabytes, probably in the order of 10 to 20 megabytes per thread of socket buffer just to hold all the packets. But because we're only sending 1 millisecond in the future, it's more on the order of like 256K to a meg, depending on the circumstance. Depends on the NIC. Yes, but we still do have to use a larger than like default socket buffer. One issue that we do have with the setup is the FQ QDisk creates some unfairness between QUIC and TCP. So if you do get into a situation where you're NIC limited, QUIC will sort of suffer relative to TCP because all the QUIC flows get as much egress out of the box as each individual TCP flow. So you're basically getting in the worst case scenario maybe 100x less throughput than TCP. In practice, you have to run your box your NIC rather stupidly hot for this to ever become a practical issue in any kind of longer term perspective. But something to be aware of. Am I doing it now? Okay. So packet sockets. Packet sockets with shared memory ring, RxRing, as I said, are a nice improvement over standard UDP sockets. We tried out TXRing, which is a memory racked transmit version. It's kind of very, very similar to RxRing, but just the opposite. And we couldn't get really a large CPU win out of them. It's not really clear why. They should work quite well. But a more important point is that they are very, very difficult to deploy. So packet sockets on the receive side basically only require you to have CapNet raw, and then you're good to go. You don't really need a whole lot of intelligence and software complexity. On the send side, you are bypassing an awful lot of awesome, cool stuff that the kernel was doing for you, and you will hate yourself. So, yeah, I mean, like including our, like all the, like it's just shocking. Like you're like, oh, I can do this, and you just, it will be bad. Like you're. So we spent a lot of time trying to one by one fix all these issues before realizing that this was a foolish idea and that we never should have gone there, and we gave up. There was a very small CPU benefit as well, the difference between like raw sockets and packet sockets, but it was not that big, and it was not worth the fact that every once in a while users had like terrible, terrible things happen to them. UDP GSO. So, at least according to Willem's recent benchmarks, UDP GSO achieves performance that's around the same as TCP for send performance. It's around 3x faster than what UDP is today. So the one quirk is it does release all the datagrams that in a send call at once. And so in order to get the full CPU savings, assuming you really wanted a 1 millisecond pacing granularity, you have to have a bandwidth of 512 megabits, which is a bit of a bummer. So you kind of have to trade off between like how bursty and lumpy am I going to go versus how much CPU savings. But it does definitely save a substantial amount of CPU. So ideally the segment could be split up in some way to really reduce loss. But it's still a great addition, and especially on high bandwidth connections, either in the future maybe client side uploads that are high bandwidth, or in data center sort of applications, it's pretty easy to get to a point where like this is a big CPU win, and you're getting either all or the majority of the benefit. Packet pacing. So for those who are at NetDev, which is not too many people, Van spent a nice hour talking. Van Jacobson spent a nice hour talking about release time-based packet pacing and how he was a big fan of this. I am also a big fan of this. It really makes it easy to integrate it with your congestion control. It's easy to reason about when the packet actually hits the wire. Admittedly, the packet might go out a little bit late, but you can basically consider NIC queuing delay as just part of the path RTT for that purpose. It would allow us to use our shared socket approach, but also control pacing in theory. So like if the FQ QDisk had a release time-based pacing module, which I'm told it should in the nearest future, then it would actually allow us to share that socket and also pace to the socket at the same time. Unlike a rate-based pacer, where if you try to share a single socket and use a rate-based pacer, there's just no correct rate that you can set for multiple flows. So disabling pacing can save us up to 30% of our CPU, which is a pretty insane number. The actual pacing CPU cost in a profile is like 1%, in terms of timers and all that junk. So it's not the direct cost. It's actually the indirect cost. It's the fact that you're bringing in a huge amount of connection state. You're sending one packet, and then you're tossing it all out, and you're just like trashed your entire CPU cache. And so, by sending, say, like 8 packets at once, or like some larger number, you're bringing connections in less often. You're getting better cache locality when they are kind of in cache because you just sent a packet, so you're kind of doing the same thing over and over again. It's fairly likely that if you're mem copying from data, that you're mem copying from an adjacent chunk of data like a moment later. All these things kind of start working for you instead of against you. But it also does increase retransmit rates about 50%, which does cost CPU, but not as much as the cache locality stuff. So I added some links to some patches. There's recent support for TX time, which is release time-based pacing. It was added to a different QDisk. I can't remember which one, but you can take a look. And there's now code in Chrome for pacing offload. So the Chromium quick implementation will do pacing offload if we have a release time-based pacer available. All right. So this is kind of my dream of sending, and it's a very approximate dream because there are a lot of details that I'm completely leaving out. But it kind of gives you an idea of where I think things are heading in the future. So you have Quick as an application. There's some set of shared memory pages. It's handing over to the networking stack a symmetric key to potentially do crypto offload. It's handing over a release time, so it can allow the packet to be released and encrypted later. And some efficient data structure, such as a timing wheel, is inside the networking stack and potentially even interacts with a hardware sort of like pacer, depending on kind of how the roles are split. And then you can offload crypto as well to the NIC if things were working out. So the thing that's hand wavy about this is there are an awful lot of details about like exactly what these APIs should look like rather. And I think that's what I and a variety of other people are trying to figure out in the next few months. Did you?
Finish your sentence. So both Inger, I was just wondering what your thoughts are about. So currently, when you do the pacing in Chromium, you delay the time at which you create the packet as a result of pacing, versus this would change to a model where you delay the time you send the packet. So I'm wondering what your thoughts about those two different models are of pacing, and which one would you lose some efficiencies as a result of that?
In applications where you think things like cancellation are going to be very likely, then you could lose a fair amount. Or cases where you're extremely sensitive to recovery time, and so the fact that like now I can't send out a retransmission until I've like cleared the buffer of the things that I already sent out. So there are circumstances where it actually could be measurably costly. So you have to kind of balance like how far in the future you want to allow yourself to pace for CPU performance with these other application metrics. But I think for so far in our initial testing for YouTube, we haven't seen any QoE changes when we've done it. Well, as long as we haven't screwed up anything else.
Lorenzo Cleary, out of curiosity, do you see timestamping happening on the left or on the right, or it doesn't matter?
I see the time coming from Quick and then the net stack actually being responsible for releasing it, I guess. Yeah.
Okay, so
because the congestion
so if it
control
sits
would
on
be
it for
Quick.
a while, then the timestamp's not accurate, and that doesn't matter, right?
Sorry, what the?
If the net stack sits on it for a while as it releases it and paste, the timestamp gets stale, but presumably that doesn't matter. Because you generate the timestamp on the left. If the pacing wheel like sits there
it's the release time, so usually it's in the future, right? So like it's intended to be.
Okay.
It's the net stack is intended to sit on it for a little bit. Cool. So there are quite a few things that still remain to be done. There's the possibility of doing some receive side optimizations. We've gone back and forth on UDP GRO. NetDev, people in NetDev had differing opinions as to whether that was a good idea at all. There's the question of what actually is the API for crypto offload whenever we do that. That's pretty wide open at this point and a pretty expensive topic. I think KTLS hopefully at least gives us an architecture for where to start in that process, but I don't know if we're going to actually adopt an extremely similar API or not. And yeah, some way to do multi-datagram UDP sends and actually have them split up is sort of a critical issue at the moment, whether it's GRO or some other mechanism. I think that's it. Oh yeah, and thank you. I want to thank all the people who have contributed to making the kernel better for Quick and for other UDP applications. So
Yeah, we have 2 minutes for questions.
Just one comment on the previous slide. So for receive path, depending on whether crypto is the bottleneck or kernel stack time is the bottleneck, with the right flags in the NIC, you're supposed to be able to get, using AFXDP, you're supposed to be able to get zero copy receive path. So basically like packet RX ring, but packet RX ring is one copy.
Yeah.
So it'd be interesting to see like what benefit like do you get by that kind of offloading versus the benefit of offloading crypto. And I'd be curious if you have an idea of the answer.
Yeah, I don't think I have any idea of what the answer is at the moment, except I can say that as long as the acceleration on a given platform is working well, whether it's ASNI or otherwise for crypto is pretty cheap. So it doesn't seem to be. The worst part about crypto is you have to touch the memory. So like, in all of this, like if you can just not touch the memory that you're trying to move around, like that's golden. that's worth a lot. So
Yeah, thank you.
Yeah. So, hi, I'm Brian, and here comes Ted. And we are going to spend the next 15 to 20 minutes talking about a bunch of things that are blindingly obvious. So we'll go fast. Come on up. This is Ted. Hi, Ted.
That's Brian. I'm Ted, and this is the worst episode of Family Guy ever.
All right. Next slide, Brian. We're gonna go real fast.
Hey, at least it's not one of the musical episodes. You don't want to hear us sing.
All right, so everyone here should remember the 1990s. This is what transport protocols looked like back then. You had transport headers for end-to-end operation. It turns out that we built a lot of stuff that also used the transport headers, like in network inspection for forwarding. I know that we didn't like to say the word NAT in the IETF in the 1990s, but it happened anyway. Filtering, measure. Oh, there's NAT. There's some modification. Various sorts of nasty and acceleration things like delaying acts and spoofing acts and doubling packets and doing other sets of wonderful stuff. And then because there was no crypto, there was a lot of deep packet inspection and random payload modification, and everyone was sad. So then we invented security, but we put what we called transport layer security around the application layer headers and payloads just to confuse everyone. We still have the transport headers for end-to-end operation. You can still do all that wonderful in-network inspection and modification on the transport headers, but now you have to do pre-shared keys or man in the middle or other things that will get you yelled down in the TLS working group in order to actually do deep packet inspection. This is where we are today. This is what an encrypted transport protocol design looks like. So QUIC is an example of this. It's sort of like the example of this right now, but it's a general pattern. You have kind of the function of the transport headers is now split between outer transport headers and inner transport headers, right? Like, so in the outer transport headers in QUIC are as little information as you can possibly expose. We've spent a lot of time talking about how little that should be. And then the inner transport headers are all of, sort of the acknowledgement, so on and so forth. And those are all encrypted. So you get the end-to-end operation on the inner transport headers. You can do in-network inspection on the outer transport headers, but no modification because the transport layer security can also be used to do end-to-end integrity protection of those headers. This is the wire image, right? It's just this blue box. Everything inside the blue box is static. This is all of that stuff that we used to have in the 90s. This is the gripping surface. What's there? The obvious part is like any information that is carried in the unencrypted bits in the protocol headers. There are a few other things here, right? Like, so the length and the entropy of all of the bits in the packet, that essentially provides an upper bound on information content, even for the encrypted bits. It does not provide a lower bound, right? So much of sort of traffic analysis resistance goes into adding length and entropy to all of the bits in all of these packets so that the upper bound is not driven by the traffic dynamics. It's driven by the dynamics of the thing doing the obfuscation. You can also do timing of packet and observation, so transmission, arrival, and these things. That gives you information about what the sender is doing, and you can maybe fingerprint the sender based on that. Why am I going through all of this review? Why does this matter? We are used to how the protocol operates being what you see on the wire. And when you have a wire image that you can design explicitly, the protocol's end-to-end operation is separate from its appearance on the wire, and it's separate from how intermediate devices interact with it. And this is new. So Ted said this at a plenary at one point. And I was like, this is new, this is different, this is novel. You've got to go in the other direction.
Because I want to go back to timing and packet observation. So I will point out that timing of packet observation may not depend solely on the protocol, but may depend on something else derived from the sender's behavior. You may have seen that there was a study a while back where somebody was able to demonstrate that they could determine what somebody was looking at from the Netflix oeuvre of a select number of Netflix series or movies, because there was a characteristic packet inter-arrival time and packet size. So it isn't just the packet wire image from a protocol perspective that has to be examined here, but really some of the wire image is derived from the sender's behavior or the recipient's behavior and acknowledgement that's still visible on the wire. And that turns out to be important because of path signals. We talked about this at a BOF which shall not be named. But in essence, when transports used to transmit clear text data on path devices, read it, and used it to create state, manage resources, and infer permission. That is, we had NATs, we had firewalls, and a whole bunch of their NFV cousins consumed the metadata as if it was intended to a signal to them. So what are explicit path signals? So when transports use encryption for metadata like packet numbers, those inferences fail. NATs, firewalls, and their kins fall back to default parameters, or, and this is where it gets even worse, they start to use the other characteristics of the wire image, like packet inter-arrival time, which may actually be content or sender behavior specific. And that has some scary consequences. Because if I'm willing to give you one set of content fast, but because I can tell that you're looking at a different set of content based on packet inter-arrival time, I give that to you slow and pace it out differently. There's some interesting policy issues around that we don't want to go to. What we'd rather see than people go out and build very expensive inferences boxes that are based on things that we don't really want them to infer from is that we switch to explicit path signals where we send data that you intend for the path to consume. Now, where does that signal go in the information to the path? Well, you could use internet layer facilities to send those signals. You could send these signals onto each transport, or you could do nothing. Wait, given where we are, you may know what our intention is. Hint, not internet area facility. Okay, so the example we talked about quick before is the example of an encrypted wire image. The latency spin bit is a quick example of an experimental piece of explicit signaling. The bit is set by the client and echoed by the server. The client changes the bit once per round trip time, and integrity is protected by each side. This exposes the round trip time to on-path observers without exposing session state when the client chooses to. That's what makes it explicit. It isn't a default in the protocol that this is always done, but the client chooses whether to start sending the spin bit, and the server chooses whether or not to echo it back. So there is unfortunately not linked to here, but some work that was recently shared over in the Quick Working Group on some tests which show that this is relatively effective, except in the case of pretty extreme reordering. And even in the case of pretty extreme reordering, there are some heuristics that you can use to determine that the cause of the failure is reordering rather than a failure of the spin bit itself. I direct you over to the Quick Working Group. I think. Oh, Marcus. Oh, sorry, I didn't see you. Marcus guest starring on today's image of the Family Guy. So this exposes the round trip time to on-path observers without exposing session state. Note, every single bit has to be designed and considered. This is explicitly added to the protocol by the designers of the protocol, and the use of it has to be explicitly considered when you're using the protocol. There's no default for what signals to send. It needs to be determined per transport. And so the use cases of specific transports may never use this. If you're inside a data center and you're using Quick and you turn on the latency spin bit, everything is going to be so quick, it's not going to change your behavior. Note the extra K on the last quick. And it needs to be optional. If a client or server don't want to send that signal, it can't be needed for session state. Remember, the whole point of this is going in the outer part, that blue bit. Here, so that it can't affect the actual functioning of the transport headers as seen from the internal. It has to be purely optional for this to work. So there are two IEB drafts on this topic, draft IEB path signals, and the soon to be renamed draft IEB Tremel/wire image. Currently Tremel, soon to be draft IEB. We are looking for comments on both of those drafts or at the mic line today.
Do we have a specific mailing list we want to send these comments to?
Architecture Discuss or stackevo@iab.org. Either would be fun.
Discuss.
Or sorry, stackevo.discuss@iab.org would also be fun. Yes, they have already put the cookies out. You're quite right.
Here comes Ronnie to go eat cookies.
Ronnie Evan, just to note that one of the issue about doing this explicit is to also to verify that there are no security or privacy issue related to that, and that's important part of this explicit signal.
Yeah, that actually should be a third point on the future version of this slide, is you actually have to think not only about how the signal is to be used, but how it could be misused, right? Because you're putting information out there. The nice thing is because of this separation here, you're not forced to leak inner information out to the path. However, if you're not careful about what you put out here, it might be just as bad, right?
So in the case of the round trip time discussion, for example, we actually had a design team in Quick that went off and looked at what could possibly be leaked by a spin bit and spent a good bit of time, most of it Brian's, trying to work out whether it could leak geolocation information, and determined that the fidelity of the geolocation that it could potentially leak was so poor compared to geolocation information you could get in many other ways that it was not an effective leak. Now, one of the difficult things about any leakage is there's always the possibility somebody will be able to put something together with other data and make new inferences that you weren't expecting if they're still in the mode of making inferences, which is one of the reasons the use of it has to be optional. If in the future somebody discovered some fingerprinting aspect of it that we were not aware of when we ran the design team, devices could decide not to set it, and the result would still be correct protocol operation from the point of view of the endpoints.
Dan Rutzer, I really like the fact that we're taking the spin bit as an example for the explicit signaling. And I really hope that we can accelerate for other bits in the future. My only concern is that if we start doing 1 bit per use case, we can end up with pretty fragmented frameworks. I don't want to rush the design to something that potentially we can think of a more extensible framework that doesn't need to be, you know, 1 use case per.
Yeah. So it turns out that 1 bit per use case is actually difficult because when you're talking about doing the analysis to figure out what, right. So basically when you're doing this, you're explicitly taking stuff that could be down here and you're moving it up here into the obvious part, right? Which means that the information is more accessible. And when you're looking at how that information is exposed in the wire image explicitly, you also have to consider how it interacts with other information that is exposed explicitly in the wire image, right? So the spin bit, like the amount of effort that we went to on the spin bit, looking at that was easy because there were no other explicit bits that we had to consider interactions with, right? So when the larger the surface that you're adding, the more sort of degrees of freedom.
Sure. I just feel like we can do the analysis on a one by one, the security and the privacy analysis, but at some point we can figure out a better way to put it into a common framework. That's all.
My name's Tim Shepard, and I listened to some of the discussion about the spin bit at the London IETF, both in the quick working group and in the hallway afterwards. And what I hadn't thought of but learned about there was that people had privacy concerns about the existence of the spin bit because it reveals the round trip time. Passive observers of the traffic on the net can discover the round trip time of a user more easily, I guess. They could probably do it anyway. But what I just realized sitting here, and you must have thought of this already, is that this design leaves open the possibility for a client to be deceptive in its setting of the spin bit, to make it appear that you have a longer or shorter round trip time. You could set it every half round trip time or a third round trip time or every 2 round trip times if for some reason you thought that was useful. I don't know if we should be concerned or happy.
So there's like and we did that work, and there's a bunch of there's some text in the drafts about sort of the model, and I won't really go into it here because we don't really want to talk about the spin bit. What we do want to talk about is sort of the general principle there is that yes, so when you separate the information here from the information here, you now have you don't even have to have an encrypted side channel. You have an encrypted channel that everyone can see, and you can coordinate here to lie about out there. Yeah, it is a general
you
pattern.
can be deceptive about things other than the spin bit.
Exactly.
On the outside. Yep.
Ben Schwartz. So I want to ask about how you generally think clients will go about making the decision to use optional explicit wire image features, the sort of reasons they might choose to enable those features, and any resultant pressures or ecosystem interactions.
So I think the decision by the client will depend on what the bit is doing, right? And so one of the things that I think you have to consider is whether a particular bit that you're proposing to send as explicit signal to the path is valuable for the client to expose or not. And so one of the questions you might ask yourself, for example, in setting a bit about round trip time is whether the client cares that the network on-path observers know the round trip time. And in this particular case, one of the reasons a client might care is it turns out that is being used in state maintenance by devices on path which are doing NAT, for example. So if you're running IPv4, you may want to expose round trip time in order that the state in NATs not age rapidly without you having to send heartbeat packets to keep the stat fresh. So there's a variety of reasons you might actually design a client to enable somebody in the network to have access to this state, but it's going to be different depending on what it is you're exposing. And you may find that there are cases where you're like, hey, I'm running IPv6, there should be no NAT in the state between me and the rest of the world. So that reason doesn't exist. So you might set it in one address family and not in another. Again, the whole design here is that with any of these explicit path signals, the client has to make the decision to set it, and it can't affect the correct operation of the protocol from the end system's perspective if it is not set.
So let me add to that. I think, so the work that I do in this is explicitly focused on measurability, and a lot of what's interesting about measurability is the ability to do diagnosis, right? So I would see in a lot of cases, there's a checkbox in the browser that says, hey, I'm having trouble. You call whoever's looking at your end-to-end path, and they say, click this box on for right now, or open a window that's in debug mode, and then try to run it. And then the devices along the path can look at the information in the debug mode window, right? So for things that are explicitly looking at diagnostics, you can essentially have sort of like in-band diagnostics targeted. And then in that case, you would expect in that case, you're adding a little bit more information than just the one bit, and then you would usually leave it off, right? So there are different bits, different complexes of bits, different use cases. Sometimes the decision goes up to UI, sometimes the decision is a system level decision, sometimes the decision is an implementation decision, and you just have to case by case.
Thank you both. I want to correct my question slightly. I should have said endpoint, probably.
Lorenzo Colletti, I know you said you don't want to talk about the spin bit, and I'm sure there are long queues at mics and lots of text, but the thing that's from the benefit of somebody who knows nothing about this, of having that perspective, seems to me that the spin bit's actually very opaque and hard to understand. And so, because if you don't look into the exact details of why the spin bit gives you these properties, it's kind of hard to understand why. And I think, so I guess the question is, if you wanted to expose the RTT, presumably there was a reason why you could have said, okay, the spin bit's 1 bit. If I want to express the RTT as 12 bits, I can't do it once every 12 packets as a 12-bit number. And I guess that kind of goes, I'm not interested in that particular engineering trade-off, but what it means is how clear does that blue have to be, right, in the outer layer, right? And if it was really more explicit, this is the RTT, would people making, for example, policy decisions around it, like do I expose this or not, would they understand better, and would that better map to the policy outcomes that you want to achieve?
It could indeed, but we have so far not been successful in coming up with a framework that would allow us to express that in a way that you could actually have a vocabulary of those things. Work continues.
The other thing to recognize is that if you wanted to send an explicit RTT as seen by the endpoint to the path and simply express it every end packets, you have different engineering trade-offs to make there. And some of those engineering trade-offs is now the packet format has to deal with that amount of variability, which is something that may not be easy for certain packet formats to deal with. And you have to deal with loss if that particular packet gets lost or suppressed. And so there's a set of issues around this where when you're doing the design of the protocol, you have to think about what the, again, what the client is going to get from this knowledge being available in the path, and from the path device's perspective, how easy it's going to be to read, and from both sides' perspective, what the parsing characteristics are. So there's a good bit of work to go into thinking about the design. And you're probably right. There's also probably some marketing, and we're probably not great for having chosen to market it as spin bit instead of RTT bit, where the spinning characteristic is how you derive the RTT. But I don't think Brian and I are likely to get better at that.
Probably derive something else from it as well. Yeah. And if it was just the RTT, maybe you couldn't. I don't know. Also, it seems to me the client gets actually nothing out of this. Only the network does, but yeah.
Well, so the client does get something out of this in the case where the network is maintaining state, because if the network stops failing to maintain state, the client's experience is better. Or if the client no longer has to send packets to maintain network state, the client's experience gets better.
Network state doesn't get cleared on the order of milliseconds. It gets cleared on the order of tens of seconds. You said that this is what you said about the NAT timeout earlier.
Well, so it depends on what and actually there's a good bit of stuff in the analysis we did for the spin bit on what the particular application characteristics are. And if you'd like to talk about that offline, I'm happy to do that. But one of the things is there are application characteristics where you don't expect the packet train to be milliseconds, but maybe many seconds before one particular side sends. And that's actually something you have to consider in this is, are there application forms where what you would get out of what you are analyzing is hiding something about the network in behavior that's actually coming from an application.
We have -2 minutes now.
We have -2 minutes. You get to be very negatively quick.
Okay. It's Chris Seals, Hutchison. Just to say I'm supportive of this. We're an operator. I'd rather have a few bits of information explicitly and optionally stated, but that I have confidence in, rather than doing something relatively expensive and computationally heuristically to infer things which you're never quite sure about. So it's better to, I mean, it actually, going back to Lorenzo's point, what's in it for the end clients is a better managed, cheaper network. So.
Thank you very much, everybody, for coming. I believe there are snacks and drinks outside.
So thank you from my side. We don't have an open mic anymore. I mean, if you want to ask me a question, you can still come and ask me questions. But like other than that, enjoy your cookies. Thank you, everybody.
Sorry, the middle box around. Oh, I was going to say, because otherwise I'm going to put a middle box right next to me.